Hello class. Today we're going to begin at the top of the second page of your momentum packet. So we're going to continue looking at the baseball and the bat hitting that baseball example that we were using the last time. Now when the bat hits the ball, we know that it imparts an impulse, a force acting in a time period to the ball, and it thus changes the ball's momentum. However, according to Newton's third law, because the bat exerts a force on the ball, then the ball must exert an equal and oppositely directed force back on the bat in the same time period. That means the bat's momentum must also change, since it had an equal and oppositely directed impulse from the ball. So, the impulse acting from the bat on the ball is equal to a change in momentum for the ball, but the equal and oppositely directed impulse from the ball on the bat will cause an equal but oppositely directed change in momentum for the bat. So the change in momentum between the ball and the bat are also equal and oppositely directed, just like the impulse. Now, does this mean that the bat will be traveling backward at the same speed as the ball? No, it does not. Because they have different masses, very different masses. Whereas the bat has a large mass and the ball has a very small mass. Since the changes in momentum are the same, to keep the equality here, the bigger mass needs to be multiplied by a smaller change in velocity, and the smaller mass would have a bigger change in velocity in order to have the same product. Now, we have defined our system as containing only the ball and the bat and nothing else. This is what we call an isolated system. An isolated system contains only those objects with which we are concerned, and the net external force acting on that isolated system is zero. Nothing outside the system, the ball and the bat, is acting on them. So, for any isolated system, if one object in the system, in this case the ball, has a change in momentum, then another object in the system, in this case the bat, would have to have an equal and oppositely directed change in momentum for the total momentum of the system to stay the same. This brings us to the law of conservation of momentum. The total momentum of the system must always remain constant if the system is isolated with no external forces acting on it. We call the law of conservation of momentum for events that take place, the initial momentum of the entire system added together, plus the final momenta of the entire system added together, must be equal at every point in time. So, if you know how many objects are in your system, then you know all their initial momentums at the beginning of an event must equal all their momenta added together at the end of the event. Momentum must be conserved. I have included a number of videos showing conservation of momentum for you to view. One good way of observing conservation of momentum is to study what happens in a special type of event called a collision. In other words, when two objects smack into each other, like the ball and the bat. There are two basic types of collisions. For both types, momentum must be conserved. It doesn't matter which kind of collision it is, momentum must be conserved. So let's take a look at both types. The first type is the elastic collision. Now, technically, these only ever happen between atomic and subatomic particles. However, we might look at billiard balls on a pool table or a baseball bouncing off a wall, we might look at those as being elastic in order to see what happens. Now, two things are true about elastic collisions. First, momentum is conserved, just as we said before. As long as the system is isolated, momentum is conserved. And also for elastic collisions, the total kinetic energy of the system is conserved. All right, then there is the other type of collision, which is inelastic. In inelastic collisions, these would be all other collisions that are not elastic. And in inelastic collisions, even though momentum is conserved, kinetic energy is not. For example, when two cars collide, you're going to lose kinetic energy to sound, or to heat from friction, or to deformation when the metal crunches. That takes energy. So kinetic energy is lost to those things during an inelastic collision. If you've ever seen slow motion of a basketball hitting the floor, it actually doesn't stay round. The ball flattens out, and then as it comes up off the floor, it reshapes into a sphere. This takes kinetic energy. So kinetic energy is converted to what we call deformation energy. So that's why the ball doesn't bounce as high as from which it dropped in such a bounce off the floor, because energy is lost to other forms other than mechanical, other than KE and PE. Now, let's take a look at an example, okay? An example would be like a 10,000 kilogram train locomotive moving along a track at 3 meters per second. It collides with a 5,000 kilogram boxcar sitting on the track at rest, and the coupling locks them together. The first thing we're asked to find is to determine the initial momentum of the locomotive. So we know that the initial momentum of the locomotive, and I'm using the L subscript to represent locomotive, would be the mass times its initial velocity. So 10,000 kilograms times 3 meters per second, we get a momentum to start with of 30,000 Newton seconds. Determining the initial momentum of the boxcar. Well, since the initial velocity of the boxcar is 0, the initial momentum of the boxcar is also 0. No motion, no momentum. Now we want to know, what is the total initial momentum of the system, the boxcar and the locomotive together? And this is before they collide. So we would simply add the two initial momenta we just found, and obviously the answer is going to be 30,000 Newton seconds. Okay, now we want to know, what is the total final momentum of the system after they collide? Well, you might be thinking, well, we don't know the final velocity of the locomotive and the boxcar, so we can't do that. Actually, yes, you can. If the sum of the initial momenta is 30,000 newtons, then according to law of conservation of momentum, the total momentum after they collide must be the same value, 30,000 Newton seconds. So this is our proof right here. This is just the mathematical statement of conservation of momentum. And in such a question, you would need to write this out as your proof for this answer, because there's no calculation to show otherwise. So this is the proof for this answer. All right, there's a little bit more to this, I believe. Okay, look at part E. It says, if they are stuck together, what is the final speed of the system? Hang on, it seems like my camera's wanting to try to focus. We'll give it a moment here. Okay, so if they stick together, that means they're like one mass after collision. So that's how I looked at it. The final momentum would be the two together traveling at one speed. Now think about this for a minute, guys. If the two objects, the locomotive and the boxcar, are coupled together, there's no way they can have different velocities. They have to have the same final velocity. So that's why we can add the masses here. and then multiply by the final speed they both have. And we know whatever this is, it has to add to the 30,000 Newton seconds we found a moment ago. So we put the masses here, and we're going to solve for the final velocity by dividing the total mass to the other side. So we get 2 meters per second for the final velocity of the boxcar locomotive system. Now, this particular part of the problem is interesting. When two objects stick together upon collision like this is a special type of inelastic collision. I'm going to go back to the previous page for just a moment and show you. Now, not all inelastic collisions do they stick together, but on some they do, and when they do, we call such an inelastic collision a perfectly inelastic collision. Okay, so this is a special case for inelastic. All right, we need to make sure we understand this is a special case for inelastic. They're not all perfectly inelastic, but some can be when they lock together like that. Another example might be a bullet fired into a wooden block. And the wooden block and the bullet go flying off together once the bullet is embedded in the block. That would also be a perfectly inelastic collision. Or maybe you're running alongside your skateboard, if any of you like to skate, and you jump onto your skateboard while it's moving. That would also be a perfectly inelastic collision, because now you and the skateboard would be considered to have one big mass between you, and therefore you're both traveling at the same speed. You have you share the total momentum together. Okay. That's as far as we're going to go in the notes for now. You've got a number of activities over the next few days looking at law of conservation of momentum and collisions, including a really cool lab. So I'll let you have at it for now. Okay? Bye-bye.